I understand.
Okay.
Thank you.
Now I think it's time. Let's look at a numeric example, which is handling the single effect evaporation system. And I have an example that I brought from one of the quizzes that we had earlier. This is the one, and I'll read it. We're talking about a single effect evaporating system, which is having the following information. The boiling temperature TB is 75. The brine rejected concentration is 75,000 ppm. The feed salinity is X feed is 45,000 ppm. Seawater is at 28 degrees centigrade. We are using steam extracted from a power plant at a temperature of 95 degrees centigrade. The capacity of the steam that we are using, I'm just modifying this, that this basically is 1 kilogram per second. It does not make a difference, by the way. It's just here that it's more realistic to be 1. The feed temperature, so the seawater has to be heated in the condenser from 28 degrees centigrade to 70 degrees centigrade. Some information are given to us here, like the boiling point elevation, overall heat transfer coefficient in the evaporator, overall heat transfer coefficient in the condenser, the HFG, latent heat of vaporization or condensation for the vapor, here is it, and the latent heat of vaporization or condensation for the steam is given here. So these are the kind of given information, and these are typically the parameters that we are looking for. Sketch the system, find the mass flow rate of the steam needed, what is the heat transfer rate in the evaporator, what is the heat transfer rate in the condenser, what is the surface area in the evaporator, surface area of the tube bundle, what is the surface area of the tube bundle in the condenser, what's the performance ratio for this unit, and what is the required cooling flow rate of the seawater to enter the condenser. So typically, these are the kind of questions that we ask when you are given, or when you are presenting a single effect evaporation, or when analyzing a single effect evaporation. I'll put this statement of the problem in Blackboard after the class. And now we need to go through the solution. So what I'm going to do is basically, I'm going to start that whiteboard. Let me first see who's missing today. We have a couple of persons missing today, I would assume. And Rashid Eliami? Not. Abdullah Al-Azwari, you are here. You asked a question at the beginning, Abdullah.
Yes, I am here.
Yes. And Muhammad Al-Ghamdi?
Yes.
Ahmed Al-Hussein?
Yes, here.
Hadi Al-Utaibi? Hadi? Abdul Karim Al-Ramadan?
Yes.
Badr?
Yes, Doctor.
Saleh?
Yes.
Saleh, you asked a question too. Usama Al-Shahrani?
Yes, Doctor.
Khalid Al-Shamrani? Khalid? Sultan Al-Suwailim?
Yes, here.
Abbas Al-Yahya?
Here, Doctor.
Okay. Hussein Al-Yusuf?
Yes, here, Doctor.
And Dawood Al-Haji?
Yes.
Okay. So, fine. Now let's look at this statement of the problem again and try to see what is the process that we do in solution. The first thing is asking for a sketch. So the sketch, basically, you are talking about two components. One of them is the evaporator. Second is the condenser. Seawater enters the condenser here, where it will be heated up from T cooling water to TF. The quantity that enters here is basically m dot feed plus m dot cooling water. And the feed temperature, part of it will be thrown away back to the sea, which is m dot cooling water. The rest is going to enter here to be sprayed in. And then what will be leaving here is basically m dot brine. And then we have steam coming from the power plant. That steam is coming with a mass flow rate m dot steam, entering with Hg and leaving with HF, saturated vapor in, saturated liquid out. So it has given off its latent heat of vaporization. And the vapor that will form here is going to be taken to condense in the condenser, and we are going to collect it as m dot distillate. There's a mist eliminator here, by the way. So that's some sort of a quick sketch of the system. Typically, what we do here for the analysis is standard. You know, it's a step-by-step thing. The first thing we do is a mass balance. So I hope you have your a sheet of paper and a pencil or a pen and a calculator. So the first thing we do is the mass balance, m dot feed. Look at the evaporator. What is entering here is we have an m dot feed entering in, which is going to be splitted. Part of it will leave as brine and part is going to be leaving as vapor. So the energy balance says that this feed, part of it is going to evaporate, which is m dot distillate or m dot vapor, and part of it is going to be rejected as brine. So this is m dot vapor or m dot distillate. We alternate between these two parameters. You can use either. And the second equation is that salinity of the feed into m dot feed is equal to the salinity of the brine into m dot brine. There's no salinity with the distillate because there is a mist eliminator to prevent the salt from leaving here. Now, what do we know here? XF is given to us. The value of XF is 45,000 ppm. Sorry, it's MB, this is XB. Let me see if I clean it further. Yes. So m dot B into XB. XB, we know it. It's given as 75,000 ppm. And we know the m dot distillate is 1 kilogram per second. So from here, simply what would I say, or what would I do? I would say that XF into m dot F is equal to m dot B, which is basically m dot F. I'm trying to eliminate it, minus m dot distillate into XB. When you look at this equation, m dot distillate is 1, XB is known, XF is known. How many unknowns we have in this equation?
Only one.
Only one unknown, which is the m dot feed. So from here, we can calculate the m dot feed. Can anyone tell me what's the m dot feed? Who can tell? مين معاه calculator يا شباب؟
2.5 kilogram.
2.5, yes, it is 2.5 kilogram per second. So this is the m dot feed, and definitely the m dot brine will be Based on this equation, this is 2.5, this is 1, so it should be 1.5 kilogram per second. Why did I start with this? Why did I start by looking at the m dot feed? Because I'm going to go through the analysis, I'm going to go through the energy balance for the evaporator. So my next step is to look at the evaporator for the energy balance. And for the evaporator, if you remember, we said that we have a steam which is going to give off its latent heat of condensation of steam. This energy is going to be utilized to heat the feed from TF to TB and evaporate some vapor. So I'm writing exactly as a description of what's happening. We're adding energy in terms of condensing steam, and this energy is going to heat that film of water over the tube surface from TF to TB, and then when it reaches the saturation temperature, part of the water is going to evaporate. Now, in the left-hand side, m dot steam is unknown, but HFG value is known. And the value of HFG for the steam has been given to us as 2260. So this is 2260. This is equal to m dot feed, which is 2.5. CP of the seawater is about 3.8, and this should be given to you, by the way, per kilogram Kelvin or centigrade. So this is multiplied by 3.8 multiplied by TB in the problem has been given to us as 75. TF has been given to us as 70 plus m dot distillate 1 into HFG has been given to us as 2324. How many unknowns we have here in this problem, in this equation? Sorry. 1. Accordingly, we can calculate the value of m dot s. Badr, you have a calculator? Badr,
Yes, doctor.
can you tell us what's the value of m dot s?
Just give me 1 second, doctor.
Okay, take your time.
$1.05 maybe.
Yeah, I'm just, let's confirm it from Badr. Shukran, ya Ahmed.
Yes, doctor. 1.05.
1.05 kilogram per second. The first thing that was needed in this problem, sketch the system, we did. The second thing is what is the flow rate of steam, which is this one. Then the third thing needed, which is going to be Q in the evaporator. By the way, we have done that. If we say that it is m dot steam into HFG of steam, then we can calculate this value. So shall we ask someone like Sultan to learn what's the value of QE? Sultan, Suelim?
Yes.
Yes. So this value HFG is 2260, HFG of steam definitely. And
H of G is 220.
so it is again?
Yes.
So the 1.05, the mass flow rate of the steam, multiplied
Yes.
HFG,
It's gonna be 2,373.
73.
Yeah, 2,373. 2373.
Yes, kilowatts. So this
Yes.
is the heat transfer rate inside the evaporator. By the way, you could also obtain it by this 2.5 into 3.8 into 5 plus 2324. It will give you the same value. So that's the second or the third requirement of this problem, which is basically this was the second and this was the third. After that, the fourth requirement is looking for Q condenser. Q condenser. How can we get this value? What will happen in the condenser?
It will heat the T cold water to T feed water.
Yes, but we don't know how much is the flow rate of the cold water. So can we get it by another way?
The
What?
heat of the latent heat of condensation.
Exactly. So it's basically going to be m dot vapor into HFG of the vapor. M dot vapor is the m dot distillate. It's the same. So the quantity is 1. And the latent heat of condensation of the vapor is this 2324. So that's basically is 1 into 2324 kilowatts. So now this is the Q or the heat transfer rate inside the condenser. Then what is needed after this is we want to get area in the evaporator. So the part number 5 here is evaporator area. Yes, يا عبد الله تفضل.
Doctor, is the MV equal exactly MD or?
It is the same. It is basically the same. It is leaving, the vapor is leaving the evaporator in a tube and it will enter into the condenser where it will condense and provide the distillate. So it's exactly the same thing.
Okay.
Now what we are looking
It
for
might be.
the area. Yes, go ahead.
I'm sorry, Doctor, but
Go ahead.
there might be يعني storage. So not all of MV will be.
No, there's no
Transform.
storage. The process basically is, if you remember from the thermodynamics, we are calling it as a steady state, steady flow process. So anything to change with time is equal to 0. So there's no storage. It's a heat exchanger. Heat exchanger does not have storage. Whatever will enter is going to leave at a constant rate.
I understand.
Okay, Abdullah, you have another question?
No, Doctor.
Okay, it's just because you. Oh, okay, fine. Okay, tamam. Now, when we are looking for an area, then we are looking basically for an expression of heat transfer rate inside the evaporator, which is nothing but the overall heat transfer coefficient in the evaporator into area of the evaporator into the temperature difference in the evaporator. And you will notice here that the temperature difference, I just put it as delta T, because if you remember from last time, we said that in the evaporator, we have steam at constant temperature, and we have the seawater coming at feed temperature. It will be heated up to TB, and then the TB will remain constant. So what I did is that I neglected this part that we have here. I neglected this portion. And I consider that the temperature difference is constant, and this is the temperature difference I put here. This is an approximately accepted. If you want to be very accurate, then you are going to divide this into 2 pieces. calculate the area associated with this from this equation, and then calculate the area associated with sensible heating. For this one, you have to do what we'll be doing in the condenser, like calculate what is the overall heat, what is the log mean temperature difference, and then calculate the required area here. But it's too small to be considered. So as a good approximation, you can just neglect it. So Q, we have calculated Q previously. We have got it from here, 2373. UE has been given to us, and the value is 2.5 kilowatt per meter square centigrade or Kelvin. And خليك معانا محمد الغامدي will ask you to calculate it. Area of the evaporator is what we need. And delta ET basically is the difference between them, TS minus TB. The values that are given to us are TS is given in the problem as 95 and TB is given as 75. From here, Muhammad, can you tell us what is the evaporator area?
47.46.
40.
7.46.
0.46. Thank you. So meter square. So this is the requirement number 5 in the problem. Then number 6.
Doctor,
Yes.
isn't TS is going to decrease while it will give heat to the vapor?
To answer your question, I'm going to do this. The steam is assumed to enter a saturated liquid, and it will leave a it will enter a saturated vapor, will leave a saturated liquid. So the temperature is?
Oh, yeah. I'm sorry.
Okay.
I'm sorry.
As a matter of fact, to make sure that no condensation is going to occur in the pipeline coming from the boiler or the turbine to the unit, we normally enter the steam slightly superheated. And to make sure that we have condensed all the steam, we make it leave slightly subcooled. But this word slightly here and slightly here is something that we neglect. I made like, we made some sort of work, research work, something like it was maybe more than 10 years ago. And then we were trying to look at the effect of desuperheating and subcooling on the performance, and we found that this effect is negligible. So that it is safe to say that we can neglect these and just assume that it is sensible. It is basically latent heat, which is just HFG. Okay. Now, number 6, we are looking at the condenser. So I will need first to know what is Q condenser. We have done that previously, and we calculated the value of Q condenser as 2324. So this is going to be in balance with overall heat transfer coefficient in the condenser into the surface area of the condenser into the log mean temperature difference in the condenser. Why log mean temperature difference? Because the vapor which is going to condense here is going to preheat the seawater from T cooling water to TF. So the seawater temperature is going to change. So the average value here is going to, or the average temperature difference is going basically to be an of the log mean temperature difference. This temperature difference we have on this side is delta T1. The temperature difference here is delta T2. Accordingly, delta T1 هادي العتيبي خليك معانا عشان تحسب لنا log mean temperature difference. Delta T1 is TV. What's TV? TV basically is TB minus boiling point elevation. TB is 75. Boiling point elevation is 1.1. So this is 73.9 degrees centigrade. So this is TV, which is 73.9, minus T cooling water, which is 28. So, معنا هادي? هادي العتيبي، وين رحت يا هادي؟ Yes, he should be here. معانا هادي ولا سبتنا؟ Okay, let's move to the next. Hussein Al Yusuf.
Yes.
Okay, can you just help us with this calculation, ya Hussein?
What should I calculate, Doctor?
We are looking for the difference here between the vapor temperature, which is 73.9, and the cooling water temperature, which is 28, which is making our delta T1 across that heat exchanger, across the condenser.
It's gonna be 45.9, Doctor.
45.9 degrees centigrade. And then the delta T2 is going to be T vapor, which is again 73.9 minus TF, which is 70. This is simple, so this is going to be
3.9.
3.9 degrees centigrade. Then the log mean temperature difference. So do we have Hadi again, or we don't have him? Hadi Rautabi? If not, برضو خليك معانا يا حسين. This is going to be delta T1 minus delta T2 divided by ln delta T1 over delta T2. So this value is going to be I think if you're using your mobile for the calculation, you have to put it in a landscape position to get the full calculator because of the ln, the natural logarithm. So معانا يا حسين؟ Seems that he's not listening. So who can provide us with this value?
It is 17.
It is 17. Yes, that's right. So the log mean temperature difference here is calculated to be
Yes, 17
degrees.
17, right.
Yes, perfect. So now we have the overall heat transfer coefficient, which is basically 2.0. We have the log mean temperature, which is 17. We have QC, which is 2324, so that now we are able to calculate area of the condenser, and the area of the condenser will be, who can tell? Who can give me this number, ya shabab?
What was the overall heat transfer coefficient for the
2. UC is 2.
Is it 68.35?
Yes, it is 68.35 meter square.
Yes.
This is the requirement number 6 here. What we need now is the PR, and to get the PR, I just need to make some space here. The steps that I'm doing here is exactly what you are going to do, and you have a similar problem. So here, looking at the value of PR, which will be requirement number 7. Let me bring the pen here. 7. PR, by definition, it is m dot distillate over m dot steam. M dot distillate, m dot steam is 1.05, if I'm not mistaken. So this is essentially 0.95, and this is typical of a system like this. Finally, cooling water flow rate in the condenser, I'll have to do it myself because we're running out of time. Q condenser is going to be m dot cooling water plus m dot feed, which into Cp, they need to be heated from T cooling water to T feed. T feed is known, 70, 2 cooling water is known, 28 degrees centigrade. Cp is known, which is 3.8 kilojoule per kilogram Kelvin. M dot feed is known, 2.5 kilogram per second. QC is known, we have calculated it here. So the only unknown here becomes the flow rate of the cooling water. When you do that, you'll find that this value is essentially, I should have it here with me. Yes, 14.56 kilograms per second. And that's what's needed. So this is basically some sort of a typical analysis for a problem of single effect evaporation. Now we have 1 minute. In this 1 minute left for us in the class, there's a couple of things I need to consider. The first one is that our second quiz is going to be a week from today. It will be on Wednesday, and it will be only on the HDH desalination system. You have your second homework with you, which is due on Monday. So it will be a problem related to that. It will be a numerical problem that you are going to solve. So we are going to make like a test or a pre-test for the setup that we talked about for the exam, which is basically I'm going to release the problem to you, and you are going to solve it on a piece of paper and then scan it and submit it. So the same information or instruction that has been, or procedure that has been sent to you to running the exams is something that you are going to entertain in that quiz. You are going to open your cameras, and the way to put the cameras is given in that sheet of procedure for exam, because we need to make a test for our midterm exam, which is coming sometime toward the end of this month, inshallah, maybe in 3 weeks' time or less. So that's something just first announcement to mention. The second is an interesting modification that is going to happen to this system. The interesting modification is the following. I'll just put the sketch and I'll leave it to you for next time to talk about it. We said that we have an evaporator and we have a condenser. And we know that the PR is basically m dot distillate over m dot steam. And in order to make the PR higher, it's either we increase the distillate or decrease the steam which is coming to us. Now we are going to work on a modification in which will enable us to make the steam less. How are we going to do that? This is it. As you will see it, there is vapor which is leaving here on the top of the evaporator. Sorry. So this is m dot steam in, and this is m dot steam out. And the brine is going to leave from here. And there is a mass which is going to enter here to condense, and then we are going to collect it here as distillate. Seawater is going to enter here. It will be preheated to feed. Part of it will be thrown away, which is m dot cooling water, and the rest is going to reach here as m dot feed. Then where's the modification? Here is it. We are going to have the vapor which is leaving here. Part of this vapor is going to be extracted, and the rest is going to come here. The part which is extracted, we are going to call it m dot entrained vapor. And the rest here is going to be m dot C, m dot condenser, which is m dot vapor minus m dot extracted vapor. The extracted vapor which is coming here, it's going to enter into a device that we call a thermocompressor. We have steam from the power plant coming here. We call it motive steam. The motive steam here, when it comes into this nozzle part, its velocity will increase up to the sonic speed and its pressure will decrease. So it's going to create a vacuum. And this vacuum is what's responsible of extracting that m dot entrained vapor here. It is going to mix with the motive steam and it will go through the diffuser part, and the diffuser part is where the velocity decreases and the pressure increases. So we call this a thermovapor compressor. And this quantity is going to be the quantity that will enter here. So m dot motive plus m dot entrained vapor. So the quantity of steam that we needed to heat the seawater, which is being sprayed here, is coming, part of it steam from the power plant, a motive steam, and part of it from the vapor that we have generated. What about the vapor that we generated? It is mixed now with the motive steam. We are going to get it back here because it will condense here. When it condenses, we are going to get it back. So m dot entrained vapor. So that at the end, we have m dot distillate here, the same value. And this is the part which is going to back again to the power plant. So I did not lose any quantity. I have just made use of some of the vapor I generated. I compressed it. We used it as a heating source, and then we took it back again. And in this case, the steam that we are getting from the power plant is basically the m dot motive steam. And accordingly, the value of PR has increased. How much did increase? You will find that next time. Today we have done a problem where the PR is 0.95. You will see by doing this, the PR is going to jump into a value of 1.5. So this is a significant improvement to the system that has occurred by just adding one device, which is that thermocompressor. We also call it ejector. And this is what we are going to discuss in detail next time, inshallah. So that would be it for today. And I'll see you next time. I'm going to remain again for about 5 minutes or so if somebody has questions.
دكتور
You may leave then.